Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark and the host of today's exciting event. I'm a professor of civil engineering at the University of Illinois and the technical director of the Fabricated Geomembrane Institute. My webcam isn't working right now, but I will get it working by the questions section at the end of the webinar. This is our first webinar of 2023, so Happy New Year, everybody. And we have already scheduled the next 6 webinars for 2023 with great speakers and timely topics. I'll show you the next webinar speaker and topic on the last slide today. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speakers will address them at the end of the webinar today. And if we don't get through them all, we will have a follow-up podcast. Viewers attending in Japan, Australia, and South Africa time zone presentations, please submit your questions during the presentation or the follow-up survey that you will receive after the webinar. And these questions will be answered during the follow-up podcast as well. So we will address all the questions from both domestic and international. Okay, a PDF of the slides today is already available in the handout section, so you can download them and follow along. In addition, in the handout section is the new biogas white paper or guideline created by the FGI, and Brian Fraser is going to talk a little bit more about that during the presentation. The recording of this webinar and a PDF of the slides and the biogas guideline will also be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to everyone who attends the entire webinar, and that should happen later today or tomorrow. Okay, today's webinar speakers, we have 2 of them. The first is Brian Fraser. Brian is Vice President of Layfield Geosynthetics and is responsible for business development in the United States and internationally. Brian has been working in the geosynthetics industry for about over 40 years, about 42 years, including manufacturing, fabrication, testing, and construction. He's written a number of papers on geosynthetics used in floating covers and other applications. Our second speaker is Steve Valero. Steve is president of BOSTD America, which is a geogrid manufacturer and a consultant to the Layfield Group. Steve has over 25 years of experience in the US and internationally, and Steve is recognized as a technical specialist in the design of geosynthetics for cover systems and retaining structures. So it's great to have Brian and Steve with us today. The title of today's webinar is Positive Pressure Anaerobic Biogas Cover Systems. Brian and Steve, thanks so much for squeezing this webinar into your busy schedules and joining us from Brian, Edmonton, Alberta, and Steve's joining us from Knoxville, Tennessee. So thanks so much for joining us, and the controls are yours.
Okay, well, thank you, Tim. It's a pleasure to be here today. And as mentioned, we'll be doing a presentation on positive pressure biogas covers. We'll look at the materials, the design components, and the various appurtenances and apparatus that go along with these cover systems. As mentioned, the FGI recently wrote a guideline for positive pressure biogas systems, which this webinar is based on. And this is available on the FGI website and the link below. So the presentation outline will cover the basics of a biological conversion process, although our expertise is not on the chemistry side, but on the geosynthetic side. And we'll look at the main functions of a biogas cover system. Steve is going to cover the design considerations, including structural, functional, operational, and safety. And then I'll cover the geomembrane material selection and testing, as well as the cover fabrication. And then we'll look at the biogas cover system installation sequencing, followed by the importance of an operation and maintenance plan for these digester covers. So in terms of the biological conversion process, as most of us know, anaerobic digestion is the process which microorganisms break down organic matter in the absence of oxygen. and anaerobic digestion converts organic materials to biogas. So these biogases are typically higher percentages of methane, normally 50 to 75%, followed by carbon dioxide. They can be 25 to 50%, and then smaller components of nitrogen, hydrogen, and hydrogen sulfide. In the lagoon treatment process, we normally see most of the solids up to 90% separated from the liquids. These biogases generated from that point are often used for electricity, heating, generating combustible motors and gas turbines. Often further downstream, we have additional biogas upgraders, which will further remove the carbon dioxide and the H2S, as well as some water. From there, we are at producing what we refer to as biofuels or biomethanes, and these are increasingly being used for fueling in fuels in transportation. The organic matter for most of these lagoon-based digesters is the concentrated animal feeding operations, as well as the food processing industry, not just on meats, but in vegetables, produce, nuts, etc., and some elements or some components from municipal waste. So the biogas cover system, we're going to be talking about flexible geomembrane cover systems. These materials require adequate flexibility and tensile strengths in combination with the ballasting and anchoring designs to withstand the internal gas pressures building up under the cover system. Covers eliminate oxygen and enhance methane production. And this methane is collected under the cover with a perimeter gas collection pipe. Covers also help to reduce odors and the release of greenhouse gases. And the biogas covers are typically larger prefabricated panels joined on site by thermal welding, and then the whole cover system floated into place on top of the wastewater. And we are talking positive pressure cover systems today. We do recognize and we do install negative air pressure systems, which we will not be talking about. So the pictures here on the left, we're just showing you an example of the photo showing the perimeter gas collection pipe and a white baffle curtain being installed. This is the actual liner system prior to the cover going on. Often we have baffle curtains fabricated and installed under the cover systems as serpentine paths. And on the right, we're actually showing the gas collection pipe again, and over here we see the floating cover, biogas cover being pulled into place. So at this point, I'm going to turn it over to Steve. Steve, you can cover the design considerations.
Thank you, Brian. So just talking a little bit about the components of biological digester with a positive pressure cover. So there are actually several more components, but we're going to focus today on the cover. But just to mention, we do normally have a base liner system to contain the liquid that's in the lagoon itself in the system, and that, you know, most commonly would be these days a geomembrane, but could also be just a simple clay soil liner, or in some cases these are even unlined still if they're legacy systems. We have the operational systems, which would include your, you know, filling and discharge components, also your gas takeaway system and venting system. And then, as Brian mentioned earlier, a baffle curtain is sometimes installed in order to eliminate short circuiting in the flow of the liquids through the system. A baffle curtain would typically be a flexible prefabricated geomembrane system, also with flotation on top and anchorage on the bottom. So next slide, please. Okay, so and then talking about the cover system, where we're going to focus today. The primary function, Brian talked about a few of the other from a functional standpoint, but the primary function with regard to structure is to capture the digester off gas and route it to a collection system, and then of course also to prevent water infiltration and limit oxygen, things of that nature that Brian had already spoke about. But from a structural standpoint, that's where our main concern is. And structural performance requirements, again, to contain the off gas and also to resist external loads without rupture or excessive deformation of the cover system. Design is typically proprietary in these cases and experience-based. There's not really any regulatory or industry standard for these cover systems. So you'll see a wide array of different systems out there in the field, and different performance requirements, all really established by the designer of record of the cover system. The primary components of a cover system would include a geomembrane, perimeter anchorage, internal ballast, and then mechanical connections and penetrations and connected to the cover system. Recommended analysis for the system, of course, you have to define and estimate the forces acting on the cover system, and then evaluate the geomembrane strength and distortion, the perimeter anchorage requirements, ballasting requirements, and ballast anchoring requirements also, and then the functional requirements, meaning the seal of the system to retain that gas that it needs to. So next slide, please, Brian. I'm talking about the forces. So we have dynamic and static forces, some well-defined, others not so much. In the dynamic realm, we have the operational pressure, of course, which is the positive pressure underneath the gas cover. This is significant, and it's typically fairly well designed or fairly well defined in design, because the owner can specify that. And of course, the mechanical engineer involved in designing the takeaway and venting system should make sure that whatever maximum and average values are given to the designer of the cover, those would be maintained during operation of the cover system. We also have environmental forces, and of course that would include wind, water, snow, ice, and other things. But for positive pressure covers, wind is really the only and primary concern of the environmental forces, because it's acting in the same direction as the internal forces under the cover. So we want to make sure that it's an additive effect and a deep stabilizing force to that cover. The other water, snow, ice landing on top of the cover actually acts to stabilize the cover. So we understand they're there, sometimes can take them into account, but in most cases, wind is really the only and primary concern of environmental forces. And of course, you have impact and abrasion. It certainly can be significant, but very difficult to characterize. And so in most cases, impact and abrasion isn't directly analyzed, included in the analysis, but they're definitely need to be accounted for, and typically are done so by using material and load safety factors during the design process. And of course, you have personnel and equipment, both during construction and during operation and maintenance of these covers, that could be walking on or in presence, adding load to that cover. Usually those are relatively small loads compared to the overall loads on the cover. So they're normally taken into account through the health and safety and operation program associated with the workers that would be normally there present working on that cover. Static loads, of course, we have the resisting forces, the uplift resistance provided by perimeter anchorage, and the ballasting that needs to be estimated. We have the self-weight of the cover system is really actually insignificant in most cases compared to the operating pressure, but nonetheless needs to be looked at and defined. And then you have the weight of ancillary components within the cover, such as mixers, electrical service lines, and hatches, access hatches, things of that nature. Also typically not a significant source of loading on the cover, but can be significant localized loading. Needs to be looked at if there's a significant localized loading, but in most cases they're just considered in terms of especially buoyancy during filling, and make sure that proper flotation is provided, especially around access hashes, things like that, where personnel might be working around those. But other than that, not explicitly taken into account for the overall design of the cover system. And then, of course, you have the potential to build up debris and soil and water on top. And again, I mentioned those are really more stabilizing forces, not necessarily good for the cover. And we'll talk about that in the maintenance and inspection part of this presentation. But from a stability standpoint, they actually act to add weight to the cover and form a stabilizing force. So they're not typically taken into account in analysis. Also, they're very difficult to characterize because you never know how much is going to be there. So moving on to the forces that we do need to characterize and how do we estimate them. I briefly mentioned the operational pressure that's typically defined by the owner or the mechanical engineer designing the takeaway system. Typical values would be right around a ½ inch of water column, or 0.02 pounds per square inch. Seems like a very small pressure, but actually it's about 10 times the weight of the typical 80 or 60 mil geomembrane that would be used for the type of cover system we're talking about. So it's significant. Wind uplift, there's again, no industry standard for wind uplift. The method used is really up to the designer. The first step in that is to determine a design wind speed, and that can be defined by code, by the literature, or by the owner. Several methods are available to take design wind speed and convert that into an uplift force. My preferred method, and probably the most commonly used method, I think, in this realm would be ASCE 7, which is your standard building code, national building code loads for structures. But basically, you have to apply appropriate factors that, a lot of these cover systems are not located in highly populated areas. There's a very minimal risk to humans with regard to the failure, structural failure of a cover. So you take that into account when applying the method. And then also you need to modify it because the ASCE 7 is really meant for buildings. And things of that nature, where this is not necessarily a building, very flexible structure, need to take into account and modify that. I typically would treat a cover system, a positive pressure cover system, as a dome or an arched roof structure with a spring line right at the ground level, and then modify and use the ASCE 7 method from there. Interestingly, just earlier last year, Dr. Lee gave a webinar presentation for FGI, and it's on FGI's website, that talks about tailoring these wind uplift estimation methods for flexible exposed geomembranes. And so I'd encourage you to take a look at that webinar as well. And it actually gives some ways to eliminate some of the conservatism and give a little more accurate estimate of uplift forces on exposed geomembranes. So it's very good information that I'd encourage you to visit and review if you're involved in this type of practice. Then Detrick 1975 method it's been applied in many past geosynthetics references, but that method I find is a very conservative estimation of uplift, and almost too conservative in order to design something that's feasible. So I rarely use it, but it is out there. You'll see it in other references. Next slide, Brian. So we also need to estimate the uplift forces in resistance and anchorage, and that's, there are several things that provide that, but primarily the resistance uplift is provided by the perimeter anchorage and the ballasting and ballast anchorage. But we also have to look at cover self-weight, or it's fairly insignificant compared to the others, but it can be taken into account as a positive and stabilizing forces. But then the cover and ballast tension anchorage is much more complex and difficult to define, mainly because these geomembranes have very low modulus compared to most structural materials the structural engineer would evaluate. And so the stretch, along with the shape of these lagoons and the way the perimeter anchorage interacts with the ballast lines and ballast anchorage, it has a fairly complex 3D interaction and load shedding that occurs, very difficult to model. So there's not really a standard approach there, but what most people will do when analyzing these is simplify the method of estimation to a two-dimensional analysis versus three-dimensional, not consider load shedding, and it makes it a fairly conservative and much simpler analysis to do. And so we want to look at, you have to determine both tension in order to determine anchorage requirements, you need to know the tension in the cover system as well as the tension in a anchored ballast system. And to do that, there are really three methods that are primarily used here. You can look at the traditional tension cable method, which has been around for hundreds of years, or at least 100 years. So looking at communication, telecommunication cable hung from poles and things of that nature. It gives a good approximation of the stress and strain and distortion in a unit width of geomembrane if we treat it two-dimensionally, but it doesn't explicitly take the flexibility of and the low modulus of the membrane into account, and therefore requires iteration to get a practical result. There's also, you can consider a flexible beam model. So in other words, treat the geomembrane or unit width of geomembrane as a very flexible beam and approximate the stress, strain, and distortion using that method. It's very simple, doesn't require iteration, and so it turns out to be a fairly representative way to model these systems. And then also you have the normalized tensile stiffness method, which Giroux et al. Published back in 1995 to look at distortion, two-dimensional distortion of a geomembrane and tension developed. Again, it requires an iterative solution, so it's a little bit more complex than the flexible beam model. All three methods essentially will produce the same results provided, and it's a very big caveat to understand that, but provided that you keep the geomembrane strength within the linear portion of the stress strain curve. So try to keep it under the yield strength and within the linear portion of the stress strain curve. If you move outside of the linear portion of the stress strain curve, you end up with results that vary widely. So again, from a design standpoint, a practical standpoint, we don't want to yield the material. Generally, the stress strain behavior can be modeled linearly when you're below the yield point of the material, or at least in the lower strain regions of the material, and therefore these methods all produce acceptable results and estimate tension in the geomembrane. Talking about perimeter anchorage, there are really two common methods that are used in this type of system. The first would be a concrete ring wall, structural concrete ring wall. It's a very effective system, very good anchorage system, but also very expensive. So it's typically confined mostly to industrial applications where they're very long term. They want a long lasting cover and not necessarily inclined to go a less expensive route. Requires structural design of the wall to handle the lateral loads at the top, and also requires structural and functional seal design of the geomembrane connection to the wall. So you have usually a batten strip and a gasket system along with bolts to make sure you get that seal. But other than that, other than the expense, a very good, very long-lasting system. More commonly, and what you mostly see in agricultural applications, is an anchor trench, a soil anchor trench backfilled with either soil or sometimes concrete added for weight. And this system basically is usually designed at the maximum load, this system is usually designed that the liner and the cover system are both included in the same anchor trench. But the cover system produces significantly more tension due to the operational pressures and wind load than the liner system. And so that's where we typically have to design the trench sizing to accommodate the cover system. Since the load due to wind is highly uncertain, we want to make sure that we, at least the best practice in this case, is design that anchor trench to basically hold up to the yield strength of the geomembrane cover system, not necessarily the estimated tension in that cover system. So of course you're going to design it at a tension lower than the yield strength of the material, but we want to design that anchor trench to actually accommodate the entire yield strength, just in case there's an abnormal event. If you dislodge if you don't want to dislodge the cover from that anchor trench, because then you risk damaging the liner system as well, and having a liquid release, which would obviously not be recommended. Industry standard is to do a two-dimensional analysis, meaning the trench is designed to accommodate the tension around the entire perimeter all at one time. And this is fairly conservative. That doesn't, obviously with wind, that doesn't normally happen that way. It's very localized, but that's the way we design. And it's a little conservative, but it can be justified. And when I go into ballast design, you'll see why. The main thing you want to do in the layout of the system, at least for the anchor trenches, avoid stress concentrations, meaning you want to radius the corners. You don't want hard 90-degree or angled corners that'll concentrate stress and tend to concentrate more force in that area of the trench system, of the liner anchor trench system, so that you don't pull that out there, liner and cover system. Mechanical anchorage can be added to the bottom if you earth anchors, helical anchors, something like that. If you don't have to limit the size of the anchorage trench, if you have very, very high tensions that you're dealing with, that can easily be done as well. Next slide, please. Just talking a little bit about mechanical connections. These have to be, there are many access hatches, mixing hatches, welds of the ballast system to the cover. You want to make sure that that tension being carried by that cover can also be carried by any mechanical connections to the cover. Otherwise, and you have an issue with potentially localized stresses being higher in these regions around these mechanical connections. So you just want to make sure you take that into account in the analysis of the cover system. Next slide, please. Also, from a functional standpoint, you've got many penetrations of these cover systems, and you want to make sure that the seals are adequate. If it's pipe type penetrations, as the outer two photos show here, simple booting systems and welding will usually accommodate the trick or do the trick there. But it needs to be flexible enough. Remember, these covers are very prone to movement under wind and operational pressure, so you need to make sure whatever booting system is used there is flexible enough to accommodate that movement. And then you also need to, obviously, the anchor trench or anchor wall, there needs to be a connection there that's leak proof. The soil anchor trenches typically seal themselves with the soil, but a concrete wall will require a gasket and a batten type seal system to make sure that you're not leaking the gas. Ballasting, really a couple of common methods. The grid ballasting, which the upper two photos kind of show examples of that. This is where you put either a, in one case you'll see a net there in a grid pattern to actually hold the cover in place. The photo to the upper left, you see a grid pattern of ballast cabling along with grout-filled or sand or water-filled tubes that create and control what we call the whales or the uplift in these systems. The lower three photos, though, the grid ballasting can be more expensive, so it's often relegated again to an industrial type environment versus agriculture. Most agricultural systems would be done with what we'd call perpendicular ballasting, which is the lower three photos that you see here, which are just strips along the short dimension, perpendicular to the long dimension and across the short dimension of the lagoon to hold maintain the shape. Typically not as effective, and you also see much higher loads if in the end anchorage of these systems because of the spans involved. And in fact, especially when you analyze some of the existing covers that are in place, it would show that these anchorage and the tensile capacity of these cable systems in the ballasting lines would not be adequate to keep the cover in place under 90 mile per hour winds or higher, which are often the case in design. So we have to ask ourselves why, though we aren't seeing multiple failures of these things. And if you go to the next slide, Brian, I'll talk a little bit about why I think. And we don't see necessarily outright failures of these cover systems, which is good. But I think it's primarily due to the flexible nature of the system itself. So some of these photos, the upper left photo here, you see what that is a concrete anchor point for a ballast system that has obviously experienced some movement, and so it's been stressed at times. So it may have not pulled out completely or failed, but it's definitely experienced some movement. So it'd be a partial failure, but not necessarily a catastrophic failure. And then also, if you hit the video here, Brian, on this slide, you just see, if you look at the inconsistent size of the whales in this particular cover systems, it seems like some, the pressure is constant under these liners, but some areas of this cover system has most likely experienced stress beyond the yield point, and therefore permanent deformation. So I think what happens in some cases is if the design wind has been experienced or the design forces have been experienced or exceeded, you can often see these sort of uneven cover systems that have obviously yielded in some areas and maybe not others. The pressure is consistent underneath, so and with the ballast line spacing is the same, they should have essentially the same size whale between each ballast line. But often, in the field, we don't see that, so it indicates it's likely that the membrane may have actually yielded. Then other things, you get some additional ballasting from, as you see, water built up on the cover down there, things of that nature. So all of this works into, it needs to be taken into account in design, that we're not seeing failures, but we need to make sure we understand the forces that are being applied here. The other thing, again, I mentioned Dr. Lee's webinar where he had talked about more accurate estimation of some of these forces, and I think it may be that we're overestimating some of the uplift forces being applied there. So again, all these things need to be taken into consideration when you're doing the design, but mainly understanding the performance requirements. Next slide, please. Recommendations for ballasting. I'll just quickly go through what we typically do for that. First off, you have to take into account the construction cost versus the risk and expense of failure. Grid ballasting is the better system with concrete ring wall, but of course, not always practical. If you're doing perpendicular ballasting, you want to make sure the layout geometry is long and narrow versus square or regular. That allows you to limit the span length on the ballast line. Create uniform cover spans where you can. That's also better to avoid horizontal stresses in the cover. Minimize the ballast line spacing to reduce cover span between the lines. And again, that reduces stress. Add internal weights if possible to add ballast and additional counteracting forces. And also allowing installation slack in those ballast anchorage lines will reduce the tension in them. So just like any cable, the more sag in the cable, the less tension. And so you can do the same thing with the ballast lines as long as it's within the parameters that you want to allow that cover to expand. Design the cover to temporarily carry the entire design load, even without the ballasting system. So you can reduce your factors of safety, but if you design the entire cover system to be below yield tension under the entire design load, then you have basically an issue where if your ballast lines do fail or get dislodged, it's a simple repair versus replacing the entire cover. And then, of course, the engineer should provide the owner and operator with maintenance and best practices and inspection guidelines to monitor performance and correct issues before, again, small things become big things. And finally, the contractor should also provide a warranty service option to the owner, which would allow for regular inspection and maintenance of this cover to, again, avoid those minor problems from becoming bigger problems. Next. Environmental and operational factors can have a significant impact on the longevity of the cover system. So the designer, the contractor, the supplier, and the owner needs to consider long-term impact of, first off, constant exposure to sunlight, elevated temperatures, which can be significant on these cover systems, and then also fatigue problems with the welds in particular on these cover systems, because they're moving around a lot. We need to constantly do inspection for small, fatigue cracking, things of that nature that might occur, and make sure those get repaired before they become major issues. And then finally, of course, abrasion and impact can also cause small pinholes and other things that need to be repaired before they become a big issue. Next. Last but not least, safety is always very important. And anytime you're working around these covers, and primarily, you're dealing with a huge volume of flammable gas. And so that needs to be taken into account with project-specific safety plans, training for personnel, and specific to fire prevention. Personnel working on these sites should have fire retardant clothing, use non-sparking equipment, make sure they have ground fault interrupted equipment, and certainly no smoking anywhere near any of these covers. And then obviously need to have good fire protection equipment or fire suppression equipment available and readily available to extinguish any fires before they become a major issue. So with that, I've covered all of my portion of the presentation, and I'll turn it back over to Brian to continue.
Okay, thank you, Steve. And we always appreciate your firsthand expertise. You've worked with us on a number of structural and civil designs, and have a lot of expertise. Moving on to the geomembrane material selection, the most common materials that we're seeing in these fabricated geomembrane digesters are linear low density polyethylene. We're seeing PVC, both unsupported or unreinforced and reinforced. We're seeing reinforced polyethylenes. We've seen EPDM rubber, and we do see some HDPE being used as well, although they are quite stiff semi-crystalline materials with low yields. So we have to go very low tensile yields. So we have to go very thick with those materials. The life expectancy of these geomembranes can vary quite substantially based on the material polymer as well as the regional application. So we can see biogas covers that last 10 years and cover systems that last up to 20 years. UV resistance is very important with these covers. They're constantly exposed. So we look closely at geographical location and soil radiation levels. Certainly the digester covers we're doing in Arizona and Texas and parts of Australia are very different than what we might see in Pennsylvania or Washington State or Canada. Temperature resistance is also very important. Looking again at the regional ambient temperatures, but more specifically at the methane temperatures. And certain phases of the digestion can see temperatures ranging from 85 degrees Fahrenheit to 130 degrees Fahrenheit. And at 130 degrees Fahrenheit, those are high long-term temperatures for the geomembrane to withstand, and it's very challenging. Chemical resistance is also very important, certainly making sure we have a membrane with noted geomembrane with noted chemical resistance to methane and the H2S gas. And as well, you should make sure you have a methane that has a very low permeability rate or vapor transmission rate, and that the manufacturer is providing adequate long-term weathering warranties. So the FGI, when we wrote our guideline last year, we definitely looked at some UV testing. We looked at a once-in-lifetime formulation, geomembrane formulation test, and accelerated UV exposure for 10,000 hours, which we then inspect the surface for cracking and surface degradation, as well as we look at tensile strengths retained, and we're recommending a minimum of 80%. We also looked at elevated temperature resistance. We looked at the oven aging testing at 85 degrees Celsius or 185 degrees Fahrenheit for 90 days. And then again, we would at that point look for any surface cracking and surface degradation. And then as well looked at the retained tensile strengths of 80% minimum. The chemical resistance, we do note again that we need good methane resistance to methane and resistant to hydrogen sulfide. And at that point, we had not listed the test methods, but the next slide will talk about that. And finally, we do note a methane permeability, the methane gas permeability to a maximum of 1,000 milliliters per meter squared per day. And many of our geomembranes can be well under that. Recently, in the last year, the Geosynthetic Institute out of Philadelphia has been working on a new test method for positive pressure geomembranes, and the method established and now officially in place is a method GM35, and it's using a QUV accelerated weatherometer, but in combination testing with pressure. So this test actually tests again the UV radiance with high UV light, temperatures of 70 degrees Celsius, with methane at 500 parts per million, so pure methane, under compression to a maximum of 3 psi. And so this would be, again, a good once in a lifetime formulation test for all geomembranes to be tested to in a positive pressure biogas covers. And so we're glad to see our industry developing a very appropriate test method. Fabrication, the in-plant fabrication is very important for these digester covers. And here again, we're doing factory welds under a controlled environment. By doing this, we often see a 75% reduction in the amount of field welding, which results in reduced construction time and cost, and overall better seam integrity. We typically are using a 2-inch factory seam, similar to what we use in the field, and thermally welded seam. And all of our factory seams are tested in peel and shear testing in accordance to the appropriate ASTM test method, whether we're fabricating a reinforced or unreinforced material. And as well, we try to prefabricate as many of the components, surface cover components as possible, including things such as the aeration mixer, access hatches, which really do require positive buoyancy, as Steve pointed out. The in-plant fabrication, as you can see, again, just a couple pictures of some of our plants, but the picture on the top left, we're welding in ideal conditions, so room temperature, clean floors, tensiometers, inline testing with the fabrication. And then these are wound up on to larger panels. We can typically, for these digester, make panels, depending on the material, weight and thickness, anywhere between 20 and 30,000 square feet. And then these large panels, as you can see on the bottom pictures, are then put on trucks and transported to site. So in terms of the sequencing of the cover installation, we follow a couple of really kind of broad steps. First and foremost, with these working with prefabricated panels, we need to have appropriate work area or laydown area on one end of the lagoon. And this is where we basically do our staging, unrolling, welding, and deployment of the prefabricated panels. And we need a dry, well-compacted area with adequate space. Second, we need good weather conditions. We really have to make sure we have a low wind event day or a couple days when we're pulling these covers over. And of course, we don't want to see a lot of rain or moisture while we're installing these. And then we have to fabricate a special reinforced leading edge. And that's our main edge that we're pulling the cover into place over the wastewater pond. With that leading edge, we need proper pulling equipment, right-sized trucks or backhoes, and heavy-duty ropes evenly spaced out in place across the leading edge. And from there, we take larger projects often require multiple fabricated panels that need to be welded together on site sequentially and then floated into place one by one or section by section. The materials then need to be properly, as soon as we have the cover pulled over, the materials need to be properly adjusted, distributed properly into the anchor trench and properly backfilled. And once we have the cover system in place and backfilled, that's when we have to start the ballasting, whether we're using webbing or strapping system or the weight systems that Steve was showing. That's very important. And all of the cover appurtenances then need to be attached. And they include things such as the mixer hatches, gas vents, gas collection pipes, emergency release vents, sludge sampling ports, and the gas testing valves. And note, it's often, once we have the cover system backfilled and we're starting to do the ballasting and venting, we actually are already seeing gases build up, as we see on the picture on the right. We're putting in some burping vents, and this installation, we already have gases building up, so it can be challenging. Picture here just shows the cover installation. So this is a picture of the unrolled accordion folded prefabricated panel in the work area, laydown area at one end prior to installation. And at this point, we're also probably fabricating this special reinforced leading edge. And the picture on the left shows this wood wrap, usually 4x4, 6x6 post, wood post, leading edge of the geomembrane. And the picture on the right actually shows the cover in place and the yellow rope showing the cover being pulled into place by equipment. We have a good video of this. Actually, we'll run it about a 220,000 square foot cover system in the Central Valley region of California. We did this job in, I think, 2019 or 2020. And here you can see our trucks and the ropes. They're on both ends, plus on the far right, we are pulling in the center with long ropes to the edge. So the superintendent says everything is safe, all good. Let's start slowly pulling the cover into place. And if you look closely, you can start to see this cover nicely tensioned, being pulled into place. We have a low wind event. This is a fairly large facility, again, about a 220,000 square foot. And we have 4 pieces of equipment slowly pulling that into place and pulling it right over top of the wastewater. And as soon as that's in place, we immediately will do the backfilling, the anchor trench backfilling. So again, once the cover is in place, it's common with the systems that we're involved with in North America that picture on the left shows a 6-inch diameter ballasting pipe filled with structural grout concrete and the ballast straps holding the piping into place, or the ballast pipe into place. And the picture on the right showing the ground anchoring and ballast pipe and chain outside of the containment area, securing this for additional load. As mentioned, we do get involved with a lot of cover appurtenances, including a lot of these covers have either floating or ground mounted fixed mixers. These are hatches for floating mixers, and these all have to require elevated foam bases to ensure we have positive buoyancy supporting the steel hatch and the floating mixer. The picture on the right actually shows elevated foam supported base we fabricated. Also, all the installation of gas vents need to be gas vents or main gas recovery. Anything penetrating the cover system needs to be properly sealed and mechanically attached for making sure that it's both air and gas tight. So as mentioned, as Steve mentioned, the operations and maintenance plan for these covers is very, very important. The biogas covers are constantly moving, ballooning, billowing, and exposed to UV wind, rain, snow temperature variances, causing thermal expansion and contraction, and all of that can accelerate the wear. So we recommend an annual inspection be performed and maintenance on these cover systems, and by a qualified geomembrane inspection company that is looking at the properly document and record all visual observations, inspect for punctures, tears, cracks, seams, and repairs. This includes all the surface cover appurtenances, the total surface area, inspecting the anchor trench, the ballasting system, and certainly any repairs performed need to be properly tested and fully documented. And of note, again, the FGI recently wrote a very good guideline on operations and maintenance, guideline for geosynthetic line reservoirs, line water reservoirs, very applicable to these digesters as well in terms of best practices and procedures. So just showing a nice picture of another example of another large digester in Central Valley region of California in full application, the ballasting, everything looking like it's working as it's supposed to. These digesters do take a very large footprint. We can see in the, for instance, in the dairy industry, we can see digesters used from as low as 300 head right up to 2,000 head. I think this is on the larger size. So you can see the large footprint of the operations, the digester up on the top left, and just a very good example of the scale and size of the many positive pressure digester covers that are being installed in North America and around the world. And another good example of in the food processing industry, this is a example of a company that manufactures figs just outside of Fresno, California. And this is a custom size and configured biogas cover that we fabricated a reinforced PVC material in a number of years ago. So at that point, Tim, I'm going to thank everybody for allowing us, Stephen and I, to present on the positive pressure biogas covers, and we'll open this up to any questions.
Great, Brian, thanks. We've got a bunch of questions. First, Brian, can you go to slide 10? And I'm going to ask you a question while you get there. Have earth anchors been used to secure the cover system?
So I'll default that over to Steve, but Steve, I'll let you answer that.
Yeah, I'm sorry. Could you repeat the question, Tim? I was unmuting.
Have earth anchors been used to secure the cover system?
Not that I'm aware of. I can't say for certain that they haven't. None that I've been involved in, but they certainly could be used in that application. Or just obviously we'd have to estimate the tension involved and then design the earth anchor for that. But certainly could be used, especially for the ballasting line. I think it'd be a good application for it. Most commonly, it's you tend to be concrete column anchors, at least in the ones that I've been involved with.
Okay.
Oh.
Thank you. Slide 10, Brian and Steve. It looked like two wires going into the end cap in the foreground. What are they? And is the larger 4 inches black pipe in the middle acting to hold the cover down and receive the siphon off the methane?
Yeah, so the two wires are actually the link of a chain that's embedded in the grout. There's grout inside of that 4-inch pipe that you see there. So the grout is essentially just, the pipe is a HDPE pipe filled with grout to provide weight. So it's purely weight, nothing to do with the methane system. And the link, what you're seeing there, what appears to be wires, is actually the link of a chain that's embedded in that grout to structurally connect it to the anchor system, which is out of view on that particular photo.
Right, so it doesn't move. Right. Okay. Next question, and I hope we can get. In Canada, would you have to meet CSA 149.6 in the design and undergo an inspection by the TSSA?
Tim, I would have to check on that. You know, we have done some of the pictures in this presentation actually were digesters done in Canada. And I don't believe it to this point we have had to, but if you, as an action, let me work with our construction group and see if that is a regulation that we're currently complying with, but I don't know the answer to that.
Okay, Mr. Furlong, we'll get back to you on that question. While I ask another question, Brian, can you go to slide 24? Next question. Is there a possibility that different whale sizes is a result of inconsistent material properties versus, say, differences in gas pressure?
In
Brian,
my
you want to
opinion,
handle it?
yeah, in my opinion, no. You know, our materials are very, very consistent. So we do see, I see, for instance, in some of the colder regions, you know, we're doing these digesters in, you know, Minnesota, some of the northern states, and in Canada. You know, we do see that we'll get some hot and cold areas, meaning more aggressive gas buildup in certain areas. And I even see that in some of the stuff we're doing in Arizona and California. So for whatever reason, we do seem to see hotter spots where we see more aggressive gas buildup. And I believe that's why we don't see necessarily a consistent positive inflation in all areas.
I think if I could add to that, just I think some other, certainly the material from a stress strain standpoint and a modulus standpoint is very consistent, almost perfectly consistent. But I think a lot of the differences you see also could relate to, as I'd mentioned, if the material had been overstressed or stressed beyond the yield point at some point in its lifetime in a particular area, it could actually stretch more in that area or have permanent deformation in that area. But more likely and more commonly, I think that these ballast lines, they're welded to the cover in places, but they can move around a little bit. So if you get either the ballast line moved or there was inconsistent spacing during construction, you can see changes in the size and how the cover blows up or these whales blow up. And then lastly, it's very difficult to get perfect tension. As you saw, Brian showed the installation video. It's very difficult to get perfect tension during installation of this cover in the anchor trench system. So it's quite likely that some of that is just the variances in slack playing out across the cover system itself. And again, not necessarily, I would say highly unlikely that it's due to material differences across the membrane itself.
Okay, great. Slide 24, which is on the screen. The pressure test is the pressure test per lot, per material? How does an owner specify a pressure test for the rolls procured for a particular digester? You know, lot, panel.
Well, again, I would write into the specification that the material needs to comply with GRI GM35, and we would have to show certification that our materials as manufacturers have been tested and have not shown burst failure. So that's first thing I would do. And of course, obviously, in addition to that, all the mechanical and endurance properties would be supplied to the engineer or owner with the mill certs. But with the mill certs, you'd want to see the GM35 certification testing. And that's, again, a once per formulation test. We'd only do that, say, once per lifetime unless we reformulated the material.
Okay, great. Attendee says safety recommend. Also, recommendation. Hydrogen sulfide may be a safety concern as well. I think early on you were talking about safety concerns, and so that might be a good one to add, hydrogen sulfide. Okay, next. Do you recommend welding the cover geomembrane to the bottom geomembrane, or should they be separate in the anchor trench?
Do you want to answer that, Brian?
Well, I'll say, I'll say we see it both ways. Certainly if we are welding the cover to the liner, I mean, that's a very critical weld. Normally we have to do 2 or 3, extrusion welds, special additional capping. So it's done commonly. Also commonly, we can see it in a existing, a common, or even a separate anchor trench. Of course, the cover, as Steve was saying, the trenching is very, very important. We need to be a deep, well-compacted trench. We need to be basically gas tight. And of course, a lot of times, in addition to just backfilling with earth, we're putting in grout and structural grout, et cetera, to help reinforce and give us the type of compaction we need. So done multiple ways or both ways.
Yeah, and I would just add, I think the leakage, even if they're not welded together, the leakage is minimal in an earthen or grouted anchor trench versus, if you've got a concrete ring wall and you've got a batten system, it's much more likely that you could, have a gasket missing or a small gap there that would lead to more leakage. So it really depends on the application and what's acceptable in terms of leakage. How critical is it to absolutely seal that up? If it's critical, then obviously they should be welded together. If it's, if a small amount of leakage is permissible, then it's a much quicker and less expensive install to not have to do a perimeter weld along, around this entire huge lagoon. So,
and I mentioned Steve too, is that the material type could make a difference, and it's interesting. Right. We see, for instance, in South America, and we see people using 30 mil, 40 mil unreinforced PVCs. So a lot of different materials with different tensile properties being used and ways of welding. So you really also have to look at the material and how we have to weld that material.
We got still a bunch more questions. Have positive pressure systems been installed without using ballast? If so, when does someone use ballast, and when can you get away with not using ballast?
In my opinion, it's really a structural problem. If you've got enough strength, say you're using a reinforced geomembrane, and you can provide enough perimeter anchorage, and it's not going to, again, sometimes the size of these whales, if you look at the center photo on this, the slide that's on the screen right now, if it's permissible to have this very large dome type structure, then it's fine. It's just, it basically comes down to the structural analysis. And if you're comfortable that the membrane itself can carry the load just through perimeter anchorage, and that load would include operational pressures as well as the environmental external loads, then it's fine. There's no necessity to provide ballast. On the other hand, if you want to control the shape of the structure, or the membrane itself is not strong enough to avoid yield under the loads, then of course you would need to add ballast to make sure that it performs as it's intended to.
Okay. Have there been any major disasters such as fires, explosions with these facilities? Is lightning or static electricity considered?
To our point, Tim, we're within Layfield. We're not familiar with any. We've heard these rumors, or we understand there. Obviously working with methane, there's that combustible risk. But of course, the way we address it with safety and et cetera, we've never experienced, nor do we know firsthand of any major failures. In terms of grounding for lightning, I don't believe that's factored into typical designs at this point.
Not in our designs anyway, but I'm sure the mechanical, the people designing the takeaway systems and whatnot are certainly providing lightning and static electricity protection to anything that's in contact with the combustible. But from I'm a civil engineer and Brian works mostly on the civil side. We don't necessarily get into the takeaway systems or the static electricity protection, things like that. So I can't necessarily say they're not designed for that. It's just not within the area that we typically work on these structures.
Yeah, we typically, as you say, Steve, we have a perimeter gas pipe. We bring the gas to a central point. We may have at that point some basic scrubbing capability, but downstream from that point, the whole mechanical system is, in that design. Yeah, I'm sure they do have, proper, lightning protection, etc. But good point, Steve.
Okay, I'm going to try to squeeze in a couple more. So, Daniel, we'll put GM16 and GM35 up with the webinar recording and the guideline and the slides. Brian, you mentioned HDPE must be very thick to use. Is 80 mil very thick, or what thickness are you thinking about?
Yeah, 80 mil is common in a cover, and normally for some of these dairy digesters that we're doing larger square footage, we'll see 80 mil. Sometimes calculations may show 100 mil with safety factor, but most common is a 80 mil cover. And again, we have to go to heavier thickness because we don't have the tensile yields in the HDP. Where again, a lot of cases with the flexible geomembranes, we can achieve extremely good tensiles with, reinforced, for instance, 45 mil materials. But I will also mention, watching what's happening around the world in Europe and parts of Europe and in South America, again, I see people using, for instance, 40 mil unsupported, and they just factor it into the digest in the ballasting, the frequency or intervals of the ballasting and the anchor trench. And so there are thinner and alternative geomembranes being used, but to your question with HDP, most covers are 80 mil.
Okay, we probably have 5 to 10 more questions. We're going to have to answer those in a podcast. If you have other questions, you can contact Brian and Steve directly. There's their email address on the screen right now, and we will answer all the remaining questions in our podcast. Brian, next slide. Our next webinar is Role of Geosynthetics in Combating the Effects of Global Warming. Tom Sangster is going to give the presentation. I saw this in Australia. It's a great presentation, Thursday, February 16th at noon Central Time. Last slide is the website. Everybody, you can visit the website under the resources menu, on top menu. Pull that down, you'll see the webinar library. All the webinars are there, including Dr. Chungling Lee's webinar that Steve mentioned is there, and this webinar will be there. So everybody, thank you so much for joining us. Brian and Steve, thanks for squeezing this webinar into your busy schedules and joining us from Edmonton and Knoxville, Tennessee. Thanks for attending, everybody.
Our pleasure. Thank you.